question, we're being given this system where we have a spring with its coefficient being k. We have our m1 over here, okay, and because there are wheels here, there's no friction over here. Then there's a string attached to m1, which goes over a pulley system, okay, so again there's no friction over here, and is attached on its other end to another mass, m2. Okay, now in our first question, we're being asked to find, okay, so at A, we're being asked to find what our point of equilibrium is, okay, so what is our value for x0? Okay, so there are two ways to do this. Our first way is to say that our sum of all of the forces is equal to 0, okay, because that's at our point of equilibrium, or to build out our equation and to find it from there. Okay, so let's do this first method first. Okay, so let's draw our force diagram. Okay, so what we can do is we can say that this is the positive x direction, okay, and then we can take a look at this. So in our rope, we're going to have tension going in this direction, okay, and then we're also going to have in one of the directions the force from our spring, okay, so the force of my spring I'm going to call Fk. Now of course this isn't frictional force because we said that there's no friction, okay, it's the force from the spring. Okay, so now if I write down my force equation for my mass number 1, so all I need is going in this direction, okay, because it's moving along the x-axis, and what's happening for m1 on the y-axis doesn't factor into my harmonic motion. Okay, it's not on the same axes. Okay, so I'm going to have t, and then as we know, when we write out our equation, okay, for our harmonic motion, when we write out the sum of all of the forces, so it always equals to negative k multiplied by x minus x0, okay? So there's always a negative over here, and then there's k multiplied by x minus x0. Okay, so this is the equation for our Fk. And then, as we said, that the sum of all of the forces is going to be equal to 0. Okay, so now we're going to take a look at our m2 and write out the force equation for that. Okay, so we're going to say that our positive y direction is in this direction, going downwards. Okay, so in that case, we have our force T in the rope going upwards, and going downwards, we have our m2g. Okay, and notice over here, our motion for mass number 2 is only in the y direction and not in the x direction, so that means we don't have to factor that in. So then, writing this out, we'll have that our m2g, because that's going in the positive direction, minus our tension is equal to 0, because the sum of all of our forces at the point of equilibrium is equal to 0. Okay, so now I can join these two equations. Okay, so I can cross out the t's on both sides, and we'll see that I get my m2g minus k x minus x0 has to equal to 0. Okay, so now I can see that my x minus x0 is equal to m2g divided by k. Okay, now I made a little bit of a mistake over here. So what we're going to do is we're going to say that over here is going to be our origin. Okay, so this is where the spring isn't being stretched or compressed. Okay, so we can say that this is called x0 tag. Okay, and if we say that this is at the origin, so it's at 0. Okay, so that means that over here this is also a tag and this is also a tag. Okay, so notice that mistake, and that means that this is also a tag. And what I'm trying to find is just my x. Okay, so that's this. So if I say that my spring is limp, okay, isn't being stretched or compressed at this point, 0, at the origin, so that means that this becomes 0. So that means that my x, okay, this, which is what I'm looking for, my point of equilibrium, so that's going to be at m2g divided by k. Okay, so that's going to be somewhere, if I draw this on the graph, it's going to be somewhere over here. Okay, so this will be my point x. Okay, so in order to get to this point x, our point of equilibrium, so what has to happen is that our spring has to stretch a little bit, okay, in order to balance out this mg over here. Okay, so that's why our point is a little bit further along. Okay, so now we're moving on to B. So in B, I'm being asked to find what is omega equal to. Okay, so here it's a little bit more complicated because we have my m1 and my m2, and they're moving on different axes. Okay, so what I'm going to do in order to find my omega, I'm going to have to find the equation for motion. Now, how am I going to find the equation for motion? I'm going to start by finding my equation for the force. Okay, so let's write out our equations. So we have the sum of all of the forces on our first body, so those are in the x direction on the first body, and that's going to be equal to, so we're going to have our t, and then again, as per usual, our fk, so that's going to be negative k, and then because we chose our x0 over here is equal to 0, so I'm just going to write out my x. Okay, and then this is going to be equal to my m1, the mass of body number 1, multiplied by its acceleration, so multiplied by x1 double dot. Okay, now the sum of all of the forces on my second body, so they're in the y direction, okay, and they are m2g minus t, okay, because the positive y direction is going downwards, and this is going to be equal to m2, and then because its acceleration is in the y-axis, so multiplied by y double dot. Okay, now because we can say that the distance between every single point on the rope is constant, okay, our rope isn't changing length, so that means that the two bodies move together, okay, m1 and m2 move at the same rate, which means that they accelerate at the same rate, okay, so that means that we can write this, x1 double dot is equal to y2 double dot. Okay, now notice if my green arrows over here representing the positive x and y directions were pointing in different directions, then we might have negative signs over here. Okay, so the relationship between our x1 double dot and our y2 double dot might involve negative signs. Okay, so now what we can do is we can join up our two equations. Okay, so as we can see, our t's cancel out, and because my x1 double dot and my y2 double dot are equal, so I can write that I have my m2g minus my kx, and this is going to be equal to my m1 plus my m2, and then multiplied by, I'll just write x1 double dot. Okay, they're being multiplied by the same thing. Okay, so now what I have to do is I have to turn this equation over here into the format for the equation, for the force equation in harmonic motion, which is this over here in red. Okay, I've put it in red because it's good if you remember this and write this down. Okay, so what we have to do is we have to put this into this format. Now it's very similar, however here we have this addition of our m2g. Okay, so I have to somehow reformat this so that it will look like this. So let's see how we do this, and it's a little bit of a trick. So because I want my coefficient over here, my k, to be on the outside of my brackets, so what I can do is take out the common factor over here, so negative k outside, because I want my negative k out. And that means that I'm going to be multiplying this by x, and then minus m2g divided by k. Okay, and then you can see if you open up this bracket, you'll get this exact thing. Okay, and then this is going to be equal to my m1 plus my m2 multiplied by my x1 double dot. Okay, and then this is obviously just my m over here from this equation. Okay, so now we can see that we're in this exact same format over here. Okay, and you can see that here my x0, okay, which over here is just my x, so let's write this, my x0, which is equal to my x over here, what we found. So we'll see we have here my m2g divided by k, which is exactly what I have over here for my point of equilibrium. Okay, so remember in this equation this is my point of equilibrium, and that's exactly what we have over here, which we found from A. Okay, so alternatively we could have just simply started answering B, and through that gotten our answer for A. Okay, but we were asked to find what our omega is, so as we know, our omega is equal to the square root of the coefficient of our x minus x0, okay? So our k, so we can see that it's k, just without the minus, divided by our coefficient of our x double dot. And here our coefficient of our x double dot is m1 plus m2. Okay? And this is the answer. Okay, so in my third question, question C, I'm being asked to find the maximum amplitude. Okay, so I'm trying to find that, such that my tension in the rope, my T, does not equal 0. Okay, so it can equal anything else, but not 0. So let's go back 1 second to our diagram. And we'll see over here, up until now, I've written out my equations for the general motion of the system. Okay, so I've said how it's built, and everything. However, I don't know yet how it's going to be moving. Okay, so what is its amplitude? Because I can stretch out, I can pull down my mass 2 downwards, okay, which will stretch my spring, okay, and my mass will move past its point of equilibrium. And then it will stretch to some kind of amplitude, and the whole system will move according to that. Okay, so now I'm trying to find what is my maximum amplitude such that my forces over here, my T, okay, aren't equal to 0. Now, what will happen when my tensions are equal to 0? That means that there's no tension in the rope, okay, which means that my rope isn't going to be taut, it's going to be loose and limp, which means that my harmonic motion will cease, okay? Because all of these equations that we've built in order to find out what our omega is and what our x is and everything, it's based, or at least our omega, it's based on the fact that our tension exists. There's tension in the rope. Okay, so in actual fact, this question is checking what the limits are. Okay, we're being asked what the limits are that I can pull my masses and play around with them such that my system will still move in harmonic motion. Okay, so if my tension can't equal 0, so in actual fact, I need my tension to be bigger than 0. Okay, so how am I going to find the amplitude? So let's go back to what we have over here with our equations for our force. Okay, so I have two equations. I have my forces on my first body and forces on my second body. Now if I look at my first equation, what I can do is I can solve this by working out what my acceleration is. Okay, so substituting this into over here, what my acceleration is, and then from that trying to isolate out my t. Or what I can do is use the second equation and isolate out my t. Okay, so what I'm going to do is I'm going to use my second equation. So let's copy it out. Okay, so I have my m2g minus t is equal to my m2 y2 double dot. And as we know from what we wrote over here, so this is also equal to my x1 double dot multiplied by m2. Okay, so I'm going to isolate out my t, and I'm going to use my x double dot. Okay, from now on, I'm going to say that my x1 double dot is just equal to x double dot. Okay, so I'll have that my t is equal to m2g minus m2x double dot. Okay, just isolate out my t from here. Okay, so what I'm going to do now is to remind you that the equation that is written in red over here is my general solution for my harmonic motion. Okay, so we already have my x0. Okay, we already found what this is. Okay, that was just this over here. Okay, or our x. So that we found already. So now what we want to do is we want to somehow write this out, okay, because I have my amplitude over here, so this is the variable I'm looking for, in order to substitute it into here. Okay, so I need to take the second derivative of this equation in order to substitute into here. Okay, so I'm just going to write it out. Okay, forget the mathematics for a second. You can do this alone if you want. So it's going to be equal to negative omega squared a multiplied by cosine of omega t plus phi. Okay, so all I've done here is I've taken the derivative of this equation twice in order to get my x double dot. Okay, so now all I have to do is I have to substitute this into my x double dot over here. Okay, so I'm going to have that my t is equal to m2g minus m2, okay, and then we have a minus and a minus, so this is plus omega squared a cosine of omega t plus phi. Okay, and then from what I said over here, this all has to be bigger than 0. Okay, this was my condition. Okay, so my key phrase over here is that my T, my tension, has to always, the key word being always, be bigger than 0. Okay, so that means that at every single time, no matter what my value for time is over here, this expression is always going to be a positive number which is bigger than 0. Okay, so how am I going to do that? So an easy way is to work out what my minimum tension is. Okay, so T min. Alright, now if my T min, my minimum tension, is bigger than 0, then any tension that is bigger than my minimum tension, so any other tension, will also therefore be bigger than 0. Okay, and that way my tension will always be bigger than 0 no matter what value for small t, for time, I plug in over here. Okay, so one way in order to find when my tension will be at a minimum is to take the derivative of this expression. Okay, so that's one way, taking the derivative, but an easier way is to check what my minimum value for cosine of omega t plus phi can be. So as we know, the minimum value that my sine or cosines can be is to be equal to negative 1. Okay, so that's the minimum value of this expression over here that it can possibly be. Okay, so then my T min, my minimum tension, is going to be equal to my m2g, and then plus my m2 omega squared multiplied by a, and then multiplied by this minimum value over here, which is negative 1. Okay, and then all of this must be bigger than 0. Okay, so now all we have to do is we have to isolate out our a. Okay, so we can write this out. So here we have a minus. Okay, this expression is a negative, so we can move it to the other side. So we're going to have that our m2g is going to be bigger than m2 omega squared a. And now I can divide both sides by my m2. Okay, and now I just isolate out my a. So I'll get that my a has to be smaller than my g divided by my omega squared. Okay, so that means that we can say that my a max, okay, so what we were trying to find over here is when it's smaller than g divided by omega squared. When the limit from the left-hand side of our amplitude, okay, when the limit is equal to g divided by omega squared, then we have our maximum amplitude, okay, and our left limit we're taking. Okay, so that's the end of this question.